So with regards to that HOLA Chem X poster, if you guys do have further questions, since I didn't have that recording when we started that up, always feel free to email me and I will try and clarify them. And I need to speak with Dr. Rastogi about the due dates that are posted online. I think he had somehow messed that up, but the on-track timing for quizzes to be due is Friday, and then as well the notebooks to be turned in by Sunday evening. So let me go ahead and type out a few students really quick to get these people to show their lab notebooks. Let's see. Okay, I'm gonna go ahead and post these names into the chat and then say, please show your pre-lab notebook, and then I'm going to open up the sharing screen. So if you have your notebook written on Word, then go ahead and show your share your Word screen and just show me your lab notebook, and then kind of just show me really quickly the pre-lab section. Whoever goes first, we'll go ahead and mark. Yeah, and if you have the physical one, you can just go ahead and put it up to the camera really quick. Okay, great. Okay, so yeah, Savannah and Tarek are good. Let me go ahead and mark those off. Great, great. Okay, and the person screen sharing, let me see, what is that name? Okay, Caleb. Awesome. Okay, thank you, Caleb. You're good. Let me see who else. Okay, Michaela. Okay, great. Thank you, Michaela. Okay, so just Erickson, Jacqueline, and Abby. Okay, Abby, great. I see this now.
How do you screen share? Oh, wait, never mind. I found it.
Okay, good. Yeah, and then go ahead and make sure within the hazard section, everyone, that we just make sure that any sort of chemicals that we be utilizing as if we were in a lab to have those listed out. Just list out every single chemical. Yeah. Okay. Good. Yes, I see it now. Yeah. Sorry, because it was usually in the table format, but that's good. Either way, whichever way, as long as that they are listed. See, the last one was Erickson. Let me see. I didn't see if he had shared yet. Let's see. Okay, well, I'll hold it until later so that way we can still keep going, and then remind Erickson to share their screen and or lab notebook later, so that way that we can validate that just for participation. And then let's go ahead and get into the important stuff for today. So we discussed the HOLA Chem X, and now we're going to go ahead and go, and I'm just going to refer you guys back to the module. I'm fairly certain that y'all already know how to access this, but just in case. Okay, multiple participants. Okay, here, I just opened up the sharing. So at the bottom, there should be on the bar, share screen, and then you'll click that, and then it'll open up a panel that shows all of the screens that you can share, Erickson. And then you just have to click on the screen. If it's your Word document screen, you click that. But if it's your camera, you would click to share camera. So I'll give you a second there if you need it to be able to share your Word document or lab notebook. I'm not sure which one that you have. Okay, well, in the meantime, I'm going to go ahead and open up the module and let him figure out the technical difficulties there. So here are our modules like we discussed last week. All the way down, sorry, section C is probably what you guys only see. And we go into here, experiment 2, TLC and column chromatography. So firstly, I would assume that y'all have already read through the lab manual, which we will be reviewing later on today. Secondly, there are a lot of videos here. This is very important to watch. They're about 20 to 40 minutes each, so we won't watch any of them today because, you know, it would be kind of a hindrance for us who've already watched them, and then for the ones that haven't, then just go ahead and utilize your time and watch these so that way that you can get a great visual on what the experiments would be like if we were performing them in the lab. So the pre-lab notebook looks like everyone did great this week. No slip ups so far. And the pre-lab quiz, make sure that you guys had already completed that. That is always due, you know, on the Friday before you come on into lab. I'm not really sure what's going on with the due dates on there because we were told to tell you guys one thing and then they're open for too long. Regardless, let's go ahead and move forward into what is important, which is after the lab day today that you guys will want to complete your post-lab notebook and turn that in by Sunday. And I believe that one has the correct date placed on it. And so right here, since online lab group C only will use the data that will be here. So let me go ahead and stop share real quick. And let's see. I'm going to briefly show you guys this because it might not make much sense until after we review the most important meat of the subject. However, this will be how you will take your information. If your first name starts with A through H, you will use part 1, I through P, part 2, and Q through Z, part 3. Secondly, same situation, A through M, part 1, N through Z, part 2. So I will explain that further once we get through the lab manual, so that way that we can go through this. Now let me go ahead and open that up. Okay. Okay, so this is a very important topic within chemistry because it will be, hold on one second, let me see what I'm saying here. Yeah, just the RF factor equation will be good. It doesn't need to be too crazy, mainly showing all of the procedure and everything that you would be performing within a lab and having all of your items and solvents listed. And we will review the RF equation as we go further down. And so the TLC and column chromatography pre-lab quiz was due Friday. And so the next lab for next week will be due this Friday. So the concept is to have your pre-lab quiz done the Friday before you come into lab. There's a whole mishap with regards to the dates on Canvas, which I will discuss with Dr. Ostogi later. But let's go ahead and focus on the topic at hand so that we can get through this because we have everyone waiting here. So let's go ahead and focus on the experiment. So this is very important to chemistry because it is the process of which that we can separate molecules and compounds, especially when we perform a reaction with A plus B converts to C. And whenever you do that, you know, you run a reaction, nothing is ideal. You know, entropy exists within the universe. So, you know, you'll have your final product, however, you'll still have a little bit of your starting material. So what would you do? How would you separate it? That's where the column chromatography comes into play, and it'll be very important, especially as chemistry majors, but as well as other biochemistry and other techniques. They will utilize other forms of column chromatography in order to separate out their compounds. So this is a very exciting technique that you guys will learn here today. It may be confusing, so I may be repeating myself over and over for you guys, but it is so that way that you guys can really understand the differences, primarily between nonpolar and polar substances. So within the word chromatography, they are stating that it is the way to describe color bands observed in a solution containing plant pigments, pass through a glass column, blah, 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 all big words. However, the most important thing that we need to get to here is mobile phase versus stationary phase, right? So thin layer chromatography, TLC for short. What we need to focus on in this situation is the stationary phase that we're going to be utilizing is a silica gel plate. which is a rectangle that you cut out of silica. Silica is polar. So remember that. Silica gel is polar, and the silica gel plate is your stationary phase. Now, our mobile phase within this type of TLC thin layer chromatography, the mobile phase is nonpolar. Your solvent is going to be moving across the plate, and it is going to be bringing your nonpolar compounds to the top of the plate, because what happens is, we want to come back to this main idea that you may all remember of hearing in Gen Chem, like dissolves like, right? Well, within that concept, if a molecule or compound is very polar, it will want to stick to your stationary phase, which is the TLC plate, because silica gel is polar. However, if it is nonpolar compound, then it will want to stick to the mobile phase, because the mobile phase in this situation would be a nonpolar solvent. So mobile, think of moving, the solvent is moving up the plate, it is the mobile phase, and the stationary phase will be the silica gel plate, which will be stationary. It sits there and it allows the solvent mobile phase to be ran across it to bring the nonpolar compounds up the plate. So that's kind of like just the gist, and I'm going to keep saying those phrases over and over so that you guys can understand the main difference between the two of polar versus nonpolar. So as we go down here, then we can go ahead and look and see that we're going to be discussing each component partitions between the two phases with different equilibrium constant or partition coefficient. The compounds separate into separate regions termed migratory bands. So right here on the left, you can see that we have a mixture, a compound mixture. Let's just say you have some reaction that you performed, right? And then you just take a drop out of there and then you put it onto a TLC plate. And here's like this first band that you have. Well, you run your solvent, which is the nonpolar mobile phase, and onto the TLC plate and up the TLC plate. And what it does is the nonpolar compounds go up. So slowly you start to see your mixture separate. And then as it runs further up the plate, your most nonpolar is here at the top, which is binding more to your mobile phase or your nonpolar solvent. And as it, the rest of them want to stick more to the silica gel. So right here at the bottom, this part of the mixture is extremely polar. So it's not binding to the solvent or mobile phase as well as it is binding to the silica gel. So with time, your mixture will separate because the more nonpolar compounds will travel up the plate, binding with the mobile phase, as the more polar compounds will be sticking to the bottom, sticking with your silica gel. And so the reason that we would understand as to why it will be sticking to these different things will be right here with regards to stating things of the attractive forces, right? So what's the reason that things bind to polar solvents or stationary phase that's polar? And that would be hydrogen bonding, right? We know it's very strong, dipole-dipole interactions. However, when we look at things like van der Waals forces, we would know that about hydrocarbons, carbon-carbon chains, very long carbon chains, thinking of things like oil, gas, petroleum ether, hexanes, etc. Things like that, very nonpolar. They don't dissolve in water. You can think about that oil-water phases that we've seen before. And the reason those two don't bind is because the oil is composed of many carbon-carbon bonds, and they are not performing any sort of hydrogen bonding, whereas the water, it has the oxygen molecules, the hydrogen molecules, and they can perform hydrogen-hydrogen bonding. So we will learn within this that it kind of overlaps with those kind of concepts of the separation of oil and water, or nonpolar and polar substances, how they can separate on thin layer chromatography. So moving forward, we can go forward to look at different sort of things. And this is just a brief overview of some other kind of separation techniques that we will not be looking deeper into this time, but they're just letting you know, the phrases, so that way in the future, when we do review those, then you guys will be aware of those. So TLC, and that's what we'll be reviewing today. Column chromatography as well will be the thing we'll review after the TLC. HPLC, or high performance liquid chromatography, not performed today, but I'm not sure if that's going to be in organic 1 or 2, but at one point you will go through that. Gas liquid partition chromatography, GLC, and gas chromatography. That will be performed later on, and we will go into deep detail since you guys won't be able to perform that in a lab, but we will go forward to understand that in the future labs. And these all involve distributions between a mobile gas phase and stationary liquid phase coated on a solid support. And so see, there's like this constant idea of the mobile phase and the stationary phase. So just keep using, that terminology in your mind and start to think about what's the mobile phase, what's the stationary phase. And then once you understand those two concepts, you'll be like, oh, okay, our mobile phase is nonpolar. Our stationary phase is polar. Like dissolves like. Polar is going to stick to our stationary. Nonpolar is going to want to go stick with our mobile phase, which is nonpolar. So moving forward, we'll get into the main concept of thin layer chromatography. And it's a form of solid liquid absorption chromatography and an important technique in organic chemistry for rapid analysis. The reason I say this is because you can literally stick a pipette into a reaction as it's been running, right? And you want to see the progress of it. And you say, okay, let me go ahead and put a spot on this TLC plate and run it. And, let's just say my reagent is extremely polar. However, whenever it combines with another molecule, then all of a sudden now you have a really nonpolar compound. Well, the new compound that you formed, you'd see one spot that's higher, nice spot up there. And then you see your starting material, a lower spot. Okay, I still have a little bit of my lower spot. So the reaction needs to run a little longer. And then eventually I'll get most of my nonpolar compound out of this reaction. And that's just a theoretical statement. So that way I can give you guys a little bit of examples. And with regards to the recordings, yeah, I need to go ahead and post them on YouTube. So I'll post last week's on YouTube, and then I'll post this one as well. And then I can just give you guys a link to that YouTube, so that way that we can view them, because Canvas, unfortunately, only has about 2 gigabytes of data. Last week's was almost 800 megabytes. So that would mean I could only upload about 3 of the videos, and that would include from the last section. So realistically, I can't upload too many of them onto Canvas. So I believe I'll just go ahead and create a YouTube channel and upload all of that for you all. So moving forward here, the main concept that we want to look at with TLC right here is putting that little spot here. We will always want to put a sample spot about 1 centimeter, 2 centimeters up from the bottom of the TLC plate. And a big concept that we want to understand is that our mobile phase or solvent that we're going to place into it needs to be below the spot that we put, because what happens is, what if you put you put too much solvent and that's up here and your spot's down here? Well, what happens if your spot is extremely nonpolar and you're putting a nonpolar solvent in there? Well, then boom, it's just going to fall all into your solvent. So that's not going to show you anything. It's not going to separate it. You're just going to be left with a polar spot on there. And so you're not going to get anything out of it. So the main thing is to make sure that your spot is pretty low, however, not lower than the solvent line that you'll be putting into the beaker. And we'll go down here and explain that a little bit later. However, where you put that spot, you run your mobile phase solvent, non-polar mobile phase into it, and it will go up. And as you see here at 2.9 centimeters, you will have a very polar compound. However, up here at 8.3 centimeters, you would notice you'd have a very nonpolar compound because it doesn't want to stick to the silica gel. So coming here, then we can go ahead and go forward and understand the concept of a developing chamber, which would be this beaker down here is the developing chamber. The chamber contains a saturated atmosphere of a suitable eluent or eluting solvent. And this word as well is, another way to state the mobile phase is the eluent or eluting solvent. It is eluting the non-polar compound from the mixture and allowing it to travel up the TLC plate. Yes, so the less polar one will be higher up the plate. So non-polar and polar are the statements here, right? So it's like when you talk about acidity and basicity, right? You would say, this is very acidic. What does acidic mean? Weakly basic, right? Extremely non-basic. When you say non-polar, polar, you can mean less polar or more polar or less non-polar or more non-polar. So it's interchangeable, and that's why we just go with the basic statement of polar and non-polar. But you have to remember, it's just like acidity that there is a scale. And thank you for reminding me of this, because I'm going to show you all at the end of this a polarity index, and that will kind of clarify everything up, because everything is not so black and white where it would just be water, and hexane, right? Because we have things like ethanol, which would be a dicarbyl uh, uh, alcohol. So you would have an ethyl alcohol, which would mean 2 carbons attached to an alcohol group, meaning that it is slightly nonpolar. However, it does experience hydrogen bonding, right? So it must be also polar. So it is a scale. And we'll definitely review polarity index at the end of this so that we can give you guys a little bit more information with regards to that. So when we take a look here and we go forward, they say also that you may place a folded filter in order to help maintain solvent equilibration in the chamber. It's not entirely necessary, but you may place it here not only to kind of hold your TLC plate in place, but also to allow the solvent to be equally distributed throughout the TLC chamber. Most commonly, we just use a beaker, and then you put your TLC plate in here, and I'm going to zoom in here so that everyone can really hit home that point. Where's our solvent? It's below the line. And that's a really extremely important thing whenever we have this in lab, because you want to make sure that those little spots don't fall into the solvent and then ruin the experiment, which is to use the TLC plate to separate our compounds here and understand how polar or non-polar that they are. The closer that they stick down to the bottom after the mobile phase has run up the TLC plate, the more polar they are because they're sticking to the silica gel. The higher that they are up onto the TLC plate, the more non-polar that they are, or the more less polar. So we will be using those interchangeable phrases in order to understand better polarity. So moving forward, this here just explains, the process of it moving up the TLC plate. So I'm not going to go too deeply into that because a lot of it's just semantics and statements. And then the most common one that we use here, silica gel. There's also alumina TLC plates. Alumina is more polar. However, more commonly in lab, we'll be utilizing the silica gel plates. So going forward, go ahead and go down. Let's see. This is just talking about how they're made and the production of them. So going to the more critical information, let's go ahead and check. The nonpolar compound and a nonpolar solvent, greater distance travel on the TLC plate. Yes. Yes. So we will also be discussing reverse column chromatography as well in the future, which will flip it, will invert everything. But we'll go ahead and discuss that further as we go down it. So let's go ahead and look here at the allotropic series shown in figure 2.4. So what does this mean? You look at it and you're like, oh my gosh, RCO2H, what does that even mean? RNH2. If you need to know what these individually are, you can Google these individually and you'll learn them. They're just some shorthand nomenclature, carboxylic acid and and alcohol here and amine here. These are just things that I know from being in chemistry for a while. But if you look these up, then it'll make more clear sense to you. The most important thing here to notice is what is here. We got 2 oxygens and a hydrogen, right? So what can we do? Hydrogen bond. So polar. If we look on the other side, well, we don't have any of that here. All we have is a halogen. R, and R's also usually indicate some sort of carbon that's just bound, and or any other miscellaneous group that's not, hydrogen, oxygen. But we notice here, there's no oxygen. And that's a very strong indicator that we're not going to experience any hydrogen bonding over here. So we would notice that this is extremely polar. And then as we go over to the right, it would become more nonpolar, or the opposite way around, extremely nonpolar. And to the left, we would become more polar, so increasing adsorption on polar stationary phases. So if we have a carboxylic acid group, for instance, something like benzoic acid, that would bind to a TLC plate like no other. You most likely wouldn't be able to even get it to go up the plate very far unless you use a very polar solvent. However, we can't go too far with polar solvents because it won't even crawl up the TLC plate. It will actually just sit. And as we go forward, we'll talk further about the solvents that we utilize on TLC plates, so I don't get too deep into there. But the main thing to take from here is the polarity index that we can look at from this right here with regards to compounds that would be placed onto a stationary phase. And eluted up with the mobile phase, a nonpolar solvent or nonpolar eluent. So going forward, then we can look here that you can see, for example, an effective eluting solvent must readily dissolve the solute, but not compete with it for binding sites on the stationary phase. So the thing in this part is what I was talking about, that if it's too polar of a solvent, then it's going to bind that plate, and we don't want that. So we want it like slightly nonpolar, but not too nonpolar where it doesn't move it. So you'll find your sweet spot there once you better understand the polarity of the molecules. So as a rule, the relative ability of different solvents to move a given substance up a TLC plate is termed eluting power, and is generally found to follow the order shown in figure 2.5. Now this is the good stuff right here. You're gonna like this stuff, trust me. So take a look here. Increasing eluting power with polar stationary phases. So as we look down here, petroleum ether, we can think of petrol, which is a statement stated for gas, gasoline, petroleum ether, hexane, toluene, DCM, dichloromethane, and this slowly is becoming more polar as we go up. Ethyl acetate. Acetone, you probably know about this nail polish remover, right? If you place that actually into water, it is miscible with water. And the reason why? Because it has a carbonyl group, which has an oxygen that readily hydrogen bonds into water. So as we go up, of course, we know ethanol, the many types of alcohol that can dissolve into water. And right here at the very top, this is one of the most polar substances, is water in and of itself. And then if we look on the other side of it, increasing eluting power with non-polar stationary phases. So if we had a stationary phase that was non-polar, which we will discuss further so I can clarify, well, what's a non-polar stationary phase? Because we only have a silica gel and alumina, and they're both polar, right? So I will explain the importance of the right arrow as we move forward, and then we can come back up to here. So let's mainly focus on the left side, right? Increasing eluting power with polar stationary phases. And so if we have a very nonpolar compound on our TLC plate, then yeah, we can go ahead and use some petroleum ether, some hexane to move it, maybe toluene. But if you have something that's in the middle and it's a little ambiguous, maybe it's a little too polar and it's sticking to that TLC plate, well, what do we use? I would shoot for something around ethyl acetate. You can also make mixtures. Ethyl acetate, hexane, very common in the lab, 30%, 50%, really great for that TLC plate. But once you start getting a little higher, and this is what I was talking about earlier, you don't want to run a TLC with acetone on silica. It's going to mess it up, it's going to smear, and it's going to stick, and it's too polar. So right here around ethyl acetate is where we want to draw the line for our silica gel as a nice eluting solvent. And so with regards to the right side, like I said, again, we will go forward to discuss that as we go deeper into the chromatography section. So we know that we put a spot on the TLC plate and it travels up as it's more nonpolar, right? Well, not all organic compounds are colored. A lot of them are colorless, transparent. So some of them, they may actually fluoresce. And you may have seen within some labs using a UV light to make something fluoresce, or you may have seen it in some science videos. Well, some of the compounds that are aromatic actually do fluoresce when you place a UV light onto it. So you put your spot on the TLC plate, you put it in the developing chamber, you allow your mobile phase to run it up, and then all of a sudden you're like, wait, where's my spot? Oh, wait, it's actually fluorescent. Put it under a UV light, turn your UV light on, and then all of a sudden you have your nice spot up there really high because it's a very non-polar compound binding to your mobile phase that is very non-polar. And so this is, just an overview. Also, one thing here, they're saying with a pencil, make sure to use pencil on these TLC plates if you're ever in a lab, because pen can actually dissolve into some of the solvents that we may use. However, pencil does not. So you would want to use pencil on a TLC plate. Going forward, some things that we may use are sulfuric acid, KMNO4, potassium permanganate, phosphomolybdentic acid, not sure about this one, and anhydride. We just utilized this one in our advanced lab the other day, where our students, they had placed a ligand on the TLC plate and you couldn't see it. All you saw was the solvent, and then once the solvent evaporated, now you don't have that little spot, right? Well, what you do is you run your TLC, you still don't see the spot, it's gone. Well, that's because it's transparent. So what do? We spray our anhydride onto the TLC plate kindly, and then place it onto a heating plate, heat it up, And then boom, you have your nice little spot there. And then that way you can know how nonpolar that your compound that you've created is as it has traveled up the TLC plate with its mobile phase. So moving forward, we'll go ahead and look at this. Chromatographic plate may be exposed to iodine vapor by placing it into a closed chamber containing several crystals of iodine. Very nice. I love using this in lab. What we do is we go ahead and, so with those fluorescent ones that we spoke about, let's just say you have 3 things in your mixture, right? And they all have varying polarity. Once you run your TLC plate, you have your 3 spots that you can see under your UV light. What you can do is you can take that and then you take a jar of iodine and then you open it up, place it in there, close it, shake it around a little bit, open it back up, use tweezers because iodine is very dangerous for your breathing and for your skin, not good for you to, have open around you. So then you use your tweezers under a fume hood and then you take it out and then you can see on your TLC plate some really nice spots. It's really good developing for it. And so, yeah, so iodine is really nice for developing those TLC plates to show those spots so that way you don't have to, just sit under a UV light in order to analyze your compound. So finally here for the TLC, what we get to in the meat of the subject is the retention factor. And here, the retention factor is the distance traveled by the substance divided by the distance traveled by the solvent. So here are some numbers, and this would be better with an image next to it. So I'm going to go ahead and scroll up here to where we had right here. This is our RF factors. This is where we started. And this one compound, more polar, was lower at 2.9 centimeters. This one has a low RF value, right? Closer to 0 means more polar. Then up here with our high RF factor, 8.3 over 12 centimeters, higher RF value means more non-polar with regards to running this solvent because the mobile phase, once again, is non-polar and our stationary phase is polar. So coming back down here, this is how you do your calculations. Very simple calculations here, just doing your distance traveled by the substance followed by the distance traveled by the solvent. Alrighty, so that pretty much concludes where our TLC is wrapped up. If you have any clarifications that you might want with regards to the TLC, always feel free to type in the chat and I'll be willing to scroll back up and take a second here and have a little more coffee. All right, column chromatography. Now, this is when we get to actually utilize TLC to our favor. So it is a form of solid liquid absorption chromatography. And so it is on the same fundamental principles of TLC. However, with regards to the way that we're going to go ahead and perform it, it is actually inverted. So it's a little confusing at first, but just stick around in it and let's look at the images so that way we can get a good digestion of what's going on here. And I would assume that in the pre-lab that you all had to see some of this, so you might already understand what's going on. But for those who don't, let's go ahead and review what's going on here. So we have here our column, as it's called column chromatography. It's a long cylinder that has a stopcock here for us to be able to elute our solvent. What you do firstly is you have a fritted disc that's at the very bottom of your column, and it's just a permanent disc. It's just like if you were filtering through a Brita filter some water. It allows the liquid to go through. However, the solids are stuck there, right? Well, our solid here, silica, just like the gel that we used on the TLC plate, it is polar. So what's going to happen in the silica? All of the polar compound is going to want to stick to the silica or be more likely to bind onto it for a longer period of time. Then we would place our mixture here, and as well the sand will be placed here, and I'll show you guys that further down. But let's go ahead and focus here that we would put our mixture or compound on the top of the silica gel. And then finally, we put our mobile phase or eluent here in order to run our mobile phase through the silica gel and bring that compound down through our column. And the plastic funnel is just for means of making sure that you get your silica gel in there kindly, because it's like sand, it's very thin. And as well, your mobile phase, your solvent, you're pouring it up high. You want to make sure that it goes in and you don't just spill solvent everywhere, be wasteful and possibly harm anything. So then it would run through and you would use a stopcock in order to turn it and increase or decrease the flow speed. And then you collect your eluent into vials, beakers, or little test tubes, depending on the quantity of the amount of solvent that you'll be running. In my lab, we run multiple grams. So we use Erlenmeyer flasks, 50 milliliters. Sometimes I do 20 milliliter fractions. Sometimes I do 50. You know, it just depends on the quantity that you're running. If you're running a very small scale reaction, which we'll look down below, then you would be using test tubes, very small 5 milliliter test tubes, which are very small because you don't have to run as much solvent, use as much silica, since it's such a smaller amount of compound, you know, so it's a relative scale, and we'll be looking at that more deeply down below. So right here, you have your mixture at the top, right, as you place it on top of your silica gel, right? And what's going to happen? Well, as it touches that silica, the polar portion of your mixture is going to want to stick to your silica. And as the time goes and your solvent is flowing through, your non-polar compounds are going to come first. So this is the portion of the TLC plate that is rising. So within the TLC, you're taking your compound and it's rising up. However, in this one, your compound is at the top coming down the silica gel. So this is the portion of the TLC that may confuse people, because you're thinking, well, wait, hold on, Scott. On the TLC plate, you're showing me that it's going up, and that's more nonpolar. But when we run our column, it goes down. Why is it running the opposite way? Well, you have to think about which way is the mobile phase flowing, right? The mobile phase is flowing downwards, coming through the silica gel and separating out all of your compound by polarity. However, on the TLC plate, your silica gel is holding it at the bottom onto your stationary phase, which is polar, and your mobile phase is coming up, running the compound up and separating it, because like dissolves like. So when we look here, as you can see, with time, you get separation components in the mixture, extremely nonpolar down here, slightly nonpolar. Remember, it's a scale. Not everything is black and white when it comes to polarity. There's a scale with regards to the hydrogen bonding and van der Waals forces. And then at the top, of course, our most polar compound is stuck to the top of the silica gel. And so let's go ahead and move forward. They're just talking about detectors and ways to see. So, you know, afterwards, once you start running your column, then you would start doing TLC, so that way that you can, you know, you can visualize it onto a plate and see, okay, I have my, you know, compound A, B, and C mixed together. Okay, compound A is coming out first, great. Well, compound A is the most nonpolar. Oh, wait, now I'm starting to see compound B, a little bit of that spot. Okay, so compound B is slightly nonpolar, but it's a little polar. Well, 20 vials later, oh, there's compound C. Where was that? Oh, it's at the bottom of the silica gel plate, the TLC plate. It's at the very bottom, even when I'm running it in the solvent system. What gives? Oh, well, it's extremely polar. That's why it took so long to come through the column. So, you know, you'll start to understand it the more and more that you visit this topic, that the polarity and the scale of it is relative to the stationary phase and the mobile phase. So always make sure to make that distinction within your head. So moving down here, alumina and silica gel are the common column chromatography stationary phase, just like TLC. You put it into your column, you get it going, you put your compound on there, and then you start separating it. The most important thing is the uniform particle size and high specific area. So when we run our columns, we want them to be as uniform as possible. The concept is that when you put your mixture on there, if you just throw it in there and you just mix it together, it's kind of like a blender. You know, you don't just toss a little bit in there and then mix it a little bit and it's done. No, you want to make it uniform. You don't want a smoothie that has your vegetables all, you know, left and right mixed up really badly. You want it to be uniform. You'd like a nice, very good smoothie. So it's kind of the same concept of when you're running your compound through your silica gel. You want to make sure that your mixture is nicely at the top, and then you can put some sand on top as well in order to make sure that whenever you add more solvent, add more of your mobile phase, that doesn't like splash your mixture up and then start separating it, and then you get some really bad separation in your column. So the most important thing, you know, is to get it really uniform and nicely onto your solid phase, which is the silica gel, the stationary phase. So with the normal phase chromatography, a polar stationary phase, alumina and silica gel, it's used in combination with organic solvents as the mobile phase or eluent, as I had discussed above, you know, using petroleum ether, hexanes, sometimes toluene, and then we start moving up towards ethyl acetate, and then we don't use anything like acetone, especially within columns, because if you use something like acetone, you can actually bind into your silica gel, and then all of a sudden you're getting silica gel coming out your column, and that's no bueno. So under these conditions, the allotropic series described for TLC in section 6.2 applies. I'm not sure what they were referring to right here, but the allotropic series up above that we had discussed regarding solvent is very important. And then this right here actually is what I was going to get you guys to look back up at the top for the reverse phase column chromatography. Now this one, you biochemists are going to love. So what we do here is we take glass beads coated with non-polar hydrocarbon film. So what happens here? It's a non-polar stationary phase. Wait, that's the opposite of a TLC. Oh, okay. So what we do is we actually can use mixtures of water and organic solvents that are polar. So let's go ahead and go back up to the top here, right? So now we can actually look here on the right, increasing eluting power with non-polar stationary phases. So if we have our glass beads coated by the hydrocarbons, then we can use things like water, methanol. I think I've heard before that methanol is a common solvent used within the biochemistry columns, the reverse phase columns. So when you think of reverse phase column, just think about the exact opposite of what we've been learning today. So the main thing we've learned today was a column chromatography, using silica gel as our polar stationary phase. We've been using non-polar eluent or mobile phase. And then as well, the opposite with regards to our reverse phase. We will have non-polar stationary phase, so we will have a polar mobile phase. So this is very important to understand the distinction between a normal column and then a reverse phase column. So coming back down here, the allotropic series then becomes a reverse. So everything that was shown above with regards to the polarity of the molecules, well, now we will understand the increasing absorption on non-polar stationary phases has reversed. So now all of your compounds that are extremely non-polar will start to bind to the column in a reverse phase column chromatography, and your more polar substances such as the carboxylic acid or your alcohol and amines down here, those will start to elute a lot faster, or they will elute the fastest relative. It'll be the exact opposite, the reverse of the regular column chromatography. So going forward, same criteria for selecting eluent for TLC applied to normal phase column chromatography. Let's see. So right here, with regards to the quantity of the silica gel that you would want to do, it is possible to use as little as 10 grams of adsorbent for each 1 gram of the mixture. But when the components of the mixture have similar polarities, and this is what I'm talking about, polarity is a scale, the ratio must be increased to as much as 100 to 200 to 1. So a ratio about 25 grams of silica to 1 gram of compound is a convenient starting point. And a general rule of thumb with regards to the height to diameter ratio, that's within the column, and the size would be about 8 to 1 with regards to how big that the column is that you're using. And if you have something that has a more of a wider scale of polarity, as they were saying, you can increase it, use more stationary phase, so that way when you're running your mobile phase through, you have more stationary phase for your more polar compounds to bind onto, and your more non-polar compounds slowly come through. Because if you don't use enough silica gel, it'll just come through as a mixture, and then you won't even have any you won't have very good chromatography going on. So going forward, the method to prepare your chromatography, one of the methods is a dry pack method. So you pour your silica gel slowly into a vertical glass column, half filled with the solvent already in there. So your mobile phase, let's just say hexane, Patron ether, is already inside of the column. You put your silica gel into there, it falls down into it, and then the other way to do it is to wet pack, which is a slurry of the adsorbent in the eluting solvent is added into the column. So this is like silica. You put silica gel and you'd mix it together and become kind of like a jelly solution, kind of liquidy and kind of wet, and then you would pour it over into the column. Both methods, the column must be constantly tapped to allow because if you kind of like toss it in, you'll get like air bubbles. And then the most important part of it is to make sure that it's all uniform. Otherwise, if you have an air bubble, your compound's traveling through, and then all of a sudden it comes to an air bubble, whoop, and just slips through, and then all of a sudden your compound mixture kind of gets mixed up within the column. So the idea is, to have a very good filter. It's just like if you have a bad filter and you have some stuff that slips through it, that's exactly what will happen here. So we always want to make sure that we have a good uniform filter going on here. Let's see. So layer of sand, this allows the sample to float evenly onto the surface of the adsorbent and prevents disruption of packing material as the eluting solvent is added. So this is what I was talking about. You're adding in the solvent from really high up above, and then it comes down and it splashes on top of your compound splashes on the walls of your column. No bueno. That's why we want to go ahead and use some sand to go ahead and help us have it packed nicely. So going forward, mixing the solvents in a minimum amount of, or mixing your compound into a very small amount of solvent and then putting it on top of your column. So this is just kind of going through the way that you pack it and everything the way that I had described. So let's go ahead and get to the important portion of this that will be here in what you would be doing if you were inside of a lab, right? So we're gonna have two compounds here. One's fluorine and one's 9-fluorinone. Let's take a look here for a second. And I kind of want y'all to just take an idea here of what you think is more nonpolar and what you think is more polar. The most critical thing here is to look at those forces that we talked about earlier, van der Waals, hydrogen bonding, things like that. If you think about that, which of these can you do hydrogen bonding with? Well, I don't see an oxygen on this one, so I'm gonna kind of just leave that there and hope that you guys pick up the hint. So let's go ahead and move forward here. So we would go ahead and set this up. I'm not gonna go ahead and read all this to you because, you guys can read it. I'm gonna go ahead and show you guys more of a picture of it, so that way that you'll get more of an understanding. And of course, watch the videos. They're really good help with this, because otherwise I'm just gonna be reading you this dry material that I've been talking about for the past 40 minutes. And it's just kind of beating the dead horse. We're not gonna do that. So we're gonna have this mixture here of the fluorine and 9-fluorinone, and it's a very small amount. So spend about 1.1 grams. So this is what I was talking about with regards to the reasoning of why everything is going to be so small. This is on a very small scale because you have a very small amount of compound mixture. So going down here, what happens is that you're going to go ahead and utilize the fluorine, the 9-fluorinone compound within your column. And what's going to happen on the column? Well, it's going to separate it by the polarity. So if you would look here, here is a sample graph, and this is important because it would show you what would happen. So to clarify this so that way you understand what this graph exactly is showing, because it's kind of a little weird. This is the first 5 milliliters that would come out of the column, and you don't really have anything. Well, this next one right here is at the 10 milliliter mark. You have one is some, and then this right here at the 15 milliliter mark, now you have a good amount, like a pretty substantial amount that you see. Then over here, 20 milliliter mark, we're back to the sum, starting to die off. And then finally over here at the 25 milliliter mark, no more left. Then we go over here, 30 milliliter, there's not really anything still. Oh, we got into the 35. Now we have some again. Now we're up to a good amount over here at 40 milliliters deep. So as you see what's happening here, as we keep increasing and going through, running our mobile phase, the nonpolar came out first, right? Then our more polar came out second. So the most important part is to understand the partitions of polarity and how everything is relative onto a scale, even though you have two compounds that, they're very, very similar in structure, but something on one of these two compounds is making it more polar. And I think if you put the puzzle pieces together today of all the things we've been talking about, you'd understand pretty easily as to why one of these is more polar than the other. So going forward, here are your post-lab questions, and you will have to answer these. Now let me go ahead and switch this screen over to, well, I can show you this actually first before we go back over to the other additional stuff that he's given. And make sure to, be original with your drawings. Please don't copy the doctor outright just because he's giving you guys this stuff as a good visual. So firstly, we have the stop clock closed, so no liquid comes through. We have our clamp holding up our column. We add in about 25 milliliters of petroleum ether. Then we dry pack it. We add our dry silica into there, and now you have a combination of petroleum ether and silica gel. Add a little bit of sand there to you know, like pack it down nicely. Then we add in our mixture of compound of solution in petroleum ether and dichloromethane. And so since it is a little bit polar, we added a little DCM so that way that it could dissolve better. And so you have your mixture of your compound in here now. Then we start to collect it, and it's starting to come down, and the mixture is starting to separate on our stationary phase by going through with the mobile phase of petroleum ether and dichloromethane. So let me switch my sharing over here really quick. And if you guys have any questions, feel free to go ahead and pop them up in the chat while I get this switched over. Okay, and so he's provided this as well, and you know, you can utilize some of this for your drawings, but just make sure you know try and be a little creative and you know make it individualized. So right here we have 3 different systems. We have one TLC chamber here that is completely 10 milliliters of only dichloromethane DCM. Then right here we have one of petroleum ether PE, 10 milliliters of that. And then we have a combination. So this is what I was talking about with regards to like ethyl acetate and hexane, combination of 75% petroleum ether or 7.5 milliliters, 25% DCM, 2.5 milliliters of DCM. And then these are just other values of mixtures that you can use, 80-20, 60-40. You know, and it's just relative to the amount of milliliters that you have of each within the solution. So what happens? Why are we doing this? Well, because we'll see going forward right here, we have our TLC plate. We make it at the exact same spot, so we have a good relative similarity between our experiments. Then we run it here at 10-15 minutes of developing it. Well, you can see right here within our first one, these spots are really close together. That's not very good. The reason it's not very good is because you want to make sure that you have them separated really nicely, so that way when you run your column, you get something that comes out firstly, and then you get something that comes out secondly. If they come out too close to each other, you might end up running it within the same vial, and then you kind of messed up the experiment, because the thing is that you want to separate them. So here in the middle, this is really nice. I would honestly, if I was running a column, I'd do this one, right? Because you have right here, your fluorine coming out first, very far and separate from your 9-fluoronones. Very nice, very good separation. This would be awesome if you were trying to separate those two. You spilled it in the lab, mixed them together, toss it up on a column, run it with your petroleum ether. Pretty nice. And then of course, you would make a mixture between petroleum ether and DCM with regards to trying to elute it at different rates. So as you can see here, this one's also, if they're this close, it's kind of like, you might want to go with something a little bit more along the lines of more petroleum ether heavy, maybe 90% petroleum ether, 10% DCM. And so again, this is the same sort of compound, you know, packing onto a column that we looked at before. So he actually drew here. This is a little bit more important with regards to the data that you guys will be analyzing. So then each test tube that you would be spotting, the first one, you wouldn't really have much, right? You get a little spot, and that would be evaporating out. The solvent evaporates away, and then you're just left with like a little bit of compound on your little plate. Second one, getting bigger, third, getting bigger. Fourth, this is when you have a lot of compound coming out of your column. And then slowly it fades out, just like the graph. It went up, some, a little bit, a lot, and then it slowly comes back down. And that would be a good column. And in good practice and research, that would be a good column. It's not as easy as this is stated though. Then after that happens, you get your more polar substance coming out, your 9-fluoronones coming out right here, a little bit, a little more, a lot, and then it slowly ramps down. So it goes up to a max capacity and then slowly tapers off until you have no more compound left onto your column. So lastly today, I'd like to just show everyone the data, and if anyone has any questions regarding polarity, then I can go ahead and clarify some of that. Otherwise, I'm going to show y'all all the data, and that way that we will understand what to do with this data. So here, like I said again, look at your first name and it will tell you which one of these is yours. And then you will utilize this for your data. Then come down here and then additionally make sure to utilize this as your data and as well to utilize this as your data, depending on your first name. Finally, I will show everyone a polarity index, and this is really some cool stuff. If you're ever involved in the science field, this is really nice. Which circles are for fluorine and non-fluorine? Kara, were you referring to the data that we were talking about, or were you referring to Dr. Okay, let me pull that back up. Okay, so down here at the bottom, with regards to this, I would say that the top portion is most likely your fluorine, and then the bottom portions are non-fluorinone. However, the clarity on here is not very good. So yeah, I would go ahead and say the top is your fluorine and your bottom is non-fluorinone. I'm not sure that on your lab manual that it is relative. Let me see what the questions are here for y'all. I'm gonna make sure, and always feel free to email me if you need any clarification. Just make sure that when you email, because if I see it, I can't. If you say, hey, Scott, I don't understand question 2. That's kind of an ambiguous thing, you know what I mean? Just if you say, hey, Scott, I don't understand. In question 2, it states, this is the question. And like, just copy and paste the question to me, and then I can give you a good, deep understanding of it. Because, these things I can express to you better than me having to pull up the whole page and have to go into it and look at it. So make sure and just, ask very descriptively what you are, trying to figure out. So let's see here, post-lab questions. Let's pop it up on screen share. Okay. So it looks like here that that data section, I don't think it is relative to these post-lab questions here. However, I think that with regards to this here, I think we may just want to go ahead and place the data that is given to you into your notebook, that as if that you had collected that data in lab, and then just go ahead and answer. Just place your numbers across it with relativity, just kind of relative to how big the spot looks, from some or none, some, a little, a lot, and then the scale how it goes back down. So just do like a relative scaling onto it, since it looks like none of the post-lab questions are relative to the data that was given. And then make sure to measure your RF values for the TLC portion as if you were in lab. Okay, so finally today, I'd like to show everyone a polarity index. This is the good stuff. Alrighty, so this is what you'll utilize in lab if you ever have to run a column, if you ever need to kind of just utilize any sort of solvents and such within reactions, or trying to figure out how to dissolve something very kindly into it. So something up here, pentane, which would be relative as it is a hydrocarbon to petroleum ether. It is up here with 0. So when we think of it, how in pH things go from acidic, like near 1, to basic, near 14, we're going to want to look at this scale right here and see that polarity ranges from 0 all the way up to H2O up here at 10. So it's a 0 to 10 scale. So the closer that you are to the lower end of the scale, the more nonpolar you are. And the closer that you are to the higher end of the scale, the more polar you are. So DMSO is up here at 7, very, 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 very polar. And then ethanol over here, alcohol is, more polar than nonpolar. And then as we go up, start getting more nonpolar, ethyl acetate, very good solvent. DCM, more nonpolar than that. Benzene, way more nonpolar, and then, goes up. Another really awesome chart is this one or this one. And this actually shows the miscibility. So right here, you can see, for instance, water. Well, what's water miscible with? Benzene? Oh, no. Don't mix those. It's not going to work. I can tell you that right now. It's just like oil and water. It's not going to mix. But water and dimethylformamide, nice. Ethanol. Everyone knows about that one. Yep, very good. So if you want to mix anything together on this chart, you can nicely look at here. Immiscible means that it won't mix with it, no matter what you want to do. However, if it's miscible, then you can combine, toluene and acetone. Sure. And look right here, acetone and water. Nice hydrogen bonding. That's good. Acetone's great. Look at it. Awesome miscibility. That's why we like to clean with it in lab. So I think that's a good stopping point for us today. If anyone has any further questions, feel free to go ahead and ask it in the chat or speak up now. And otherwise, we are good to go, and you guys can head out.
Thank you.
Mm-hmm. Yes. You too. Thanks.
Can you hear me?
Yes.
Okay.
Yes, I can.
On the procedure part for the TLC, it says that we're supposed to place one pencil dot about 1 centimeter from the left side and 1 centimeter from the end, and then do the same with the right side. But in the video, it just did 1 dot at 1.5 centimeters from the bottom. So which procedure do I include in my pre-lab notebook for my procedure?
The original one. The video is just a deeper explanation, and relative to the distance that you place it on the TLC plate, as long as it's not too far up the TLC plate, you'll get a good separation onto your TLC plate. So the primary situation is that you don't want it too high, because then you won't get good separation as the mobile phase and nonpolar solvent goes up. But you don't want it too low to where the mobile phase submerges that line, because then the compound can actually just mix directly into the solvent.
Okay, and then the same goes for the wait time, because I know the video did 15 to 20 minutes, but the procedure just says like wait till the solvent line's 2 to 3 millimeters from the top. So
yeah.
it would be
I follow the procedure. In lab, it varies. Some solvents, due to density, they travel different times. So that time frame is kind of just a statement. But the realistic factor is, if you were in a lab, you would want to go ahead and stop it before it reaches the top, so that way that you get a line. And the reason that we want to stop it before it hits the top is so you can get that RF value. Because if it hits the top, it's been described to me that it can just keep running. The solvent just keeps going. And so, yeah, you want to have like 2 to 3 millimeters from the top as a stopping point, so that way you can draw a line across it and then calculate your RF. So that one is the correct answer.
Okay, all right, thank you.
Okay, does anyone else have any further questions before I close out? Alrighty, everyone have a nice day.